Hello there, and welcome back to Sleepy Tinfoil Hat. Tonight we are going to drift into one of those subjects that sits right on the edge between science, mystery, and the kind of ideas that make people lean back in their chair and quietly wonder if there is more going on behind the scenes than we are told. We are going to talk about energy that may exist everywhere. Energy that does not come from burning fuel, not from sunlight, not from wind, but from the very fabric of space itself. The kind of energy that sounds impossible at first, yet keeps showing up in serious physics papers, old patents, and strange stories connected to NASA, secret laboratories, and experiments that never quite made it into the headlines. When people first hear the phrase zero-point energy, it sounds like something from science fiction, like the power source of a spaceship that never runs out of fuel. But the strange part is that the idea did not come from science fiction at all. It came from quantum physics, from scientists trying to understand what happens when everything is cooled down as much as possible, when motion should stop, when energy should be gone, and yet something still remains. That tiny leftover energy, the one that refuses to disappear, became one of the most mysterious concepts in modern science. Before we go deeper, if you enjoy these quiet explorations into hidden science, forgotten theories, and the strange corners of physics that most people never hear about, make sure you subscribe to Sleepy Tinfoil Hat and leave a comment telling me where in the world you are listening from tonight. I always like to imagine these stories drifting out across the planet, reaching someone in the middle of the night, somewhere far away, listening with the lights off, just letting the mind wander. And now, you do not need to do anything else. Just settle in, relax your shoulders, let your breathing slow down, and we will begin. The idea behind zero-point energy starts with a simple question that physicists asked more than 100 years ago. What happens when something has no energy left at all? In classical physics, the answer seemed obvious. If you remove all heat, all motion, all vibration, then the system should stop completely. Absolute zero temperature, the coldest possible state, should mean total stillness. Nothing moving, nothing changing, nothing happening. But when quantum mechanics entered the picture, the universe stopped behaving in such a simple way. Scientists discovered that even at absolute zero, particles do not stay perfectly still. They cannot. The laws of quantum physics say there is always a tiny amount of motion, a tiny amount of energy that cannot be removed. This leftover energy became known as zero-point energy, the lowest possible energy a system can have, and yet it is not zero at all. At first, this seemed like a small technical detail, something only mathematicians would care about. But as the equations became more precise, something strange appeared. The empty space itself, the vacuum, the place where there should be nothing, was not actually empty. According to quantum theory, space is full of tiny fluctuations, little bursts of energy appearing and disappearing constantly, too small to see directly, but always there. This idea changed the way scientists looked at the universe. Instead of empty space being truly empty, it became more like a restless ocean, always moving, always shifting, filled with invisible energy. Even in a perfect vacuum, even with no atoms, no light, no heat, the equation said energy was still there, hiding in the background. For most physicists, this was just part of the math. Something interesting, but not something you could use. The energy was there, but it was thought to be impossible to extract. Like knowing there is motion in the air around you, but having no way to turn it into electricity. The vacuum energy became one of those strange facts that lived in textbooks, but never seemed to have a practical purpose. But not everyone saw it that way. Some scientists and some engineers started to wonder what would happen if the equations were telling the truth in a more literal sense. If space really contains energy everywhere, in every direction, all the time, then in theory, that energy would be the largest energy source in the universe. Larger than stars, larger than nuclear reactions, larger than anything we normally use. And once that idea appears, it becomes very hard to forget it. Because if energy exists everywhere, then someone, somewhere, would eventually try to find a way to tap into it. And that is where the stories begin to get strange. Over the decades, rumors started appearing about experiments that never fully explained their results. Patents that described devices that seemed impossible. Research programs that quietly started, then quietly disappeared. And every so often, the name NASA would appear in the background, connected to studies of vacuum energy, advanced propulsion, and physics that sounded just a little too far ahead of its time. NASA, after all, has always lived on the edge of what is possible. Their job is to build machines that leave the Earth, to send instruments into space, to solve problems that most scientists never even need to think about. And when you are working at that level, sometimes you end up exploring ideas that sound unbelievable to everyone else. In the late 20th century, a small number of papers began circulating inside advanced physics circles, talking about the possibility that vacuum fluctuations might not just be theoretical. Some researchers suggested that under certain conditions, these tiny quantum movements could produce measurable forces. Others proposed that the vacuum might contain enormous energy density, far more than anything we normally deal with, but locked in a form that is extremely difficult to access. One of the effects often mentioned in these discussions is something called the Casimir effect. It sounds complicated, but the idea is strangely simple. If you place two metal plates extremely close together, closer than the width of a human hair, something unexpected happens. The quantum fluctuations between the plates become slightly different from the fluctuations outside them. The result is a tiny force pushing the plates together, as if empty space itself is pressing on them. This effect has been measured in real experiments, not science fiction, not theory, but actual laboratory work. The force is small, very small, but it proves something important. It proves that the vacuum is not nothing. It proves that empty space can create a physical effect, something you can measure, something you can detect. And once scientists saw that, the old question came back again, the one that never quite goes away. If empty space can push on metal plates, if the vacuum contains energy, if quantum fluctuations are real, then could there be a way, somewhere, somehow, to use that energy for something larger? Most mainstream physicists say no. The energy is there, but it cannot be extracted in a useful way. The laws of thermodynamics seem to prevent it. Every time someone proposes a machine that claims to pull energy from the vacuum, it ends up not working, or not working the way it was described. The universe, at least according to accepted physics, does not allow free energy. But history is full of ideas that were once impossible until someone found the one detail everyone else missed. And that possibility, even if it is small, has kept the idea of zero-point energy alive for decades. There are stories of research groups studying unusual propulsion systems, looking for ways to move spacecraft without carrying large amounts of fuel. There are papers discussing whether space itself could be used as a source of momentum, or whether quantum fields could create forces that do not behave like ordinary mechanics. Most of these studies are theoretical, quiet, hidden inside technical journals, but every so often, one of them catches attention because of who funded it, or where it came from. And every time NASA appears in those documents, people start to wonder again. Because NASA does not usually spend time on ideas that have no chance at all. And that is where the subject becomes perfect for nights like this, when the world is quiet, when the mind is slow, when it feels possible that somewhere behind the ordinary explanations, there might be deeper layers of reality still waiting to be understood. Tonight, we are going to keep drifting deeper into those layers, into the physics of the vacuum, the experiments that hint at hidden energy, the strange connections between quantum theory and space travel, and the quiet rumors that some discoveries may have gone further than we were ever told. So just let your thoughts float. Let the questions stay unanswered, and we will keep moving slowly into the mystery. The more physicists studied the vacuum, the stranger it began to look. In everyday life, empty space feels like the simplest thing imaginable. When you remove all the air from a container, when you take away all matter, all light, all heat, what remains should be nothing at all. Just a quiet, motionless void. But quantum physics refuses to allow that kind of perfect stillness. According to the equations, even the most perfect vacuum imaginable is never truly empty. It is filled with constant activity, tiny fluctuations that appear and vanish so quickly that they cannot be seen directly, yet their effects can still be measured. These fluctuations come from what physicists call quantum fields. Instead of thinking of the universe as made of solid particles moving through space, modern physics describes everything as fields that exist everywhere at once. There is an electron field, a photon field, a quark field, and many others. Even in a region where there are no particles at all, the fields are still there, quietly vibrating at the lowest level they are allowed to have. That lowest level of vibration is what gives rise to zero-point energy. One of the strange rules of quantum mechanics is that you can never remove all motion from a system. If a particle were perfectly still, its position and momentum would both be known exactly, and that would violate the uncertainty principle. Because of this, the universe always keeps a tiny amount of motion, a tiny amount of energy, no matter how cold or empty a system becomes. It is as if reality itself refuses to be completely silent. When scientists began calculating how much energy might exist in the vacuum, the numbers became almost unbelievable. Depending on how the math is done, the energy density of empty space could be enormous, far greater than the energy contained in all the stars in the universe. Most of this energy cannot be used, at least not in any way we understand, because it exists in a perfectly balanced state. The fluctuations cancel each other out, leaving no obvious way to extract power from them. Still, the fact that the energy appears in the equations at all was enough to keep the idea alive. If the vacuum contains energy, then the vacuum is not just a background. It becomes something active, something real, something that might interact with matter in ways we do not fully understand yet. In the mid-20th century, as space exploration began to move from imagination into reality, some scientists started thinking about these ideas in a more practical way. Rockets require fuel, and fuel is heavy. The heavier the spacecraft, the harder it is to launch, and the farther you want to travel, the more fuel you need to carry. This problem has always been one of the biggest limits on space travel. If there were ever a way to draw energy from the environment itself, from space instead of from fuel tanks, it would change everything. NASA, along with other research organizations, occasionally looked into very unconventional ideas, not because they expected them to work, but because the reward would be so enormous if even one of them turned out to be possible. Most of these studies stayed quiet, buried inside technical reports, because they dealt with concepts that sounded too speculative for the public to take seriously. One area of interest involved the possibility that quantum fluctuations could produce tiny forces that might be amplified under the right conditions. The Casimir effect, which had already been measured in laboratories, showed that the vacuum could push objects together when they were extremely close. The force was very small, but it proved that empty space could influence matter in a measurable way. Some researchers wondered if there might be other vacuum effects that had not been discovered yet, effects that might be stronger or that might behave differently under extreme conditions. There were also discussions about whether the vacuum might play a role in gravity itself. In some theories, gravity is not just a force between masses, but a result of how energy interacts with space-time. If the vacuum contains energy everywhere, then that energy might contribute to the structure of space itself. Some physicists even suggested that understanding vacuum energy could be the key to unifying quantum mechanics with general relativity, something scientists have been trying to do for more than a century. These ideas were not secrets, at least not in the strict sense. Papers were published, conferences were held, and small research programs were funded from time to time. But they were not the kind of work that made headlines. Most people never heard about them because the results were uncertain, the math was complicated, and the conclusions were often incomplete. Still, every now and then, a document would surface that sounded more ambitious than usual. Reports talking about advanced propulsion concepts, studies exploring whether space itself could provide momentum, discussions of energy systems that did not rely on chemical reactions or nuclear fuel. Whenever those papers mentioned vacuum energy, or zero-point fields, or quantum fluctuations, they would attract attention from people who believed that something important might be hiding behind the technical language. One of the reasons these stories keep coming back is that the physics itself really is strange enough to leave room for imagination. When scientists say that empty space is full of energy, they mean it literally, even if that energy cannot normally be used. When they say particles can appear out of nowhere for a fraction of a second, they are not speaking metaphorically. Quantum theory allows that kind of behavior, as long as it happens within the limits set by the uncertainty principle. In laboratories, these effects are usually tiny. They show up as small shifts in energy levels, slight forces between objects, subtle changes in how particles behave. But the equations do not say the effects must always be small. They only say that under normal conditions, the fluctuations average out. If the conditions were different enough, if the fields could somehow be disturbed or unbalanced, then the results might be different as well. That possibility has led to decades of speculation about whether the vacuum could ever become a practical energy source. Most attempts to build so-called free energy devices have failed, often because they misunderstood the physics or ignored the limits imposed by thermodynamics. The laws of energy conservation are very strict, and they have survived every serious test so far. That is why most physicists remain skeptical whenever someone claims to have found a way to pull unlimited energy from empty space. But skepticism does not mean the subject is closed. Even today, serious researchers continue to study vacuum energy, not because they expect to build impossible machines, but because the concept is too important to ignore. It appears in cosmology, in particle physics, in theories about the origin of the universe itself. Some scientists believe that the expansion of the universe may even be driven by vacuum energy, a mysterious pressure sometimes called dark energy, pushing space apart on the largest scales. If that idea is correct, then the energy of the vacuum is not just a small detail. It becomes one of the dominant forces in the cosmos, shaping the evolution of galaxies, stars, and the universe as a whole. And once again, the thought appears, quietly, in the background. If the vacuum can influence the entire universe, what else might it be able to do under the right conditions? For organizations like NASA, questions like that are impossible to completely ignore. Their mission has always required thinking about what seems impossible at first. Every spacecraft, every probe, every experiment in orbit depends on pushing technology beyond what existed before. Even if most unconventional ideas never work, the few that do can change everything. Because of that, small studies into advanced physics never fully stop. They come and go, funded for a few years, then replaced by something else, then revisited later when new theories appear. From the outside, it can look like nothing happened. From the inside, it is part of a long process of slowly testing the limits of what nature allows. And when the subject is something as strange as zero-point energy, the limits are not always obvious. There are still unanswered questions about the vacuum, about why it contains the energy it does, about how that energy relates to gravity, and about whether the equations we use today tell the whole story. Physicists are used to living with questions like that. The deeper they look, the more complicated the universe becomes. So tonight, as we keep drifting through these ideas, it is enough to simply notice how unusual the picture really is. Space that is not empty. Energy that cannot be removed. Forces that appear out of nothing, then disappear again. And somewhere in the background, the possibility that we may not yet understand everything the vacuum can do. As the study of quantum physics continued through the late 20th century, scientists slowly became more comfortable with the idea that the vacuum was not truly empty. What had once sounded like a strange mathematical trick started to feel more like a real property of nature. Experiments kept confirming that tiny fluctuations existed, that particles could briefly appear and vanish, and that empty space itself could produce measurable effects under the right conditions. None of this meant unlimited energy was waiting to be collected, but it did mean the universe was far less simple than it first appeared. One of the reasons this subject never completely disappeared is because it connects to so many different areas of physics at the same time. Zero-point energy is not just about energy sources. It appears in atomic physics, in cosmology, in the theory of black holes, and even in attempts to understand how the universe began. Whenever scientists try to describe the very smallest scales of reality, the vacuum always seems to be there in the background, quietly influencing everything. In quantum field theory, every point in space is filled with fields that can never be completely turned off. Even when no particles are present, those fields still have a lowest possible energy level. That lowest level is the zero-point energy. The strange part is that the total energy predicted by the equations is incredibly large, so large that it creates one of the biggest unsolved problems in physics. When physicists compare the theoretical energy of the vacuum with the amount of energy that seems to exist in the real universe, the numbers do not match at all. The difference is enormous, far beyond what anyone expected. This mismatch is sometimes called the vacuum catastrophe, because the theory predicts far more energy than the universe appears to contain. Some scientists believe this means the calculations are incomplete. Others think there must be some unknown mechanism that cancels most of the energy out. And a few wonder if the energy is really there, but hidden in a way we do not yet understand. Whenever a mystery like that exists, it naturally attracts curiosity. Not only from physicists, but from engineers, inventors, and people who believe that hidden physics might lead to new technology. The idea that space itself could contain vast amounts of energy is too interesting to ignore completely. Even if most attempts to use it fail, the possibility keeps returning again and again, every few decades, often in slightly different forms. During the early years of the space age, NASA and other research groups occasionally explored ideas that sounded unusual at the time. Some of these were related to propulsion, because propulsion is one of the hardest problems in space travel. Rockets work by pushing mass in one direction to move the spacecraft in the other. That means you always need fuel, and the more fuel you carry, the heavier the spacecraft becomes. It is a cycle that limits how far and how fast you can go. Because of that, scientists sometimes look at concepts that do not rely on traditional fuel at all. These ideas are usually very theoretical, but they are still studied because the reward would be enormous if any of them turned out to be possible. Some proposals involved manipulating space-time itself. Others looked at whether electromagnetic fields could produce thrust without propellant. And occasionally, the discussion would return to the vacuum and the question of whether the energy of empty space could play a role. In the 1990s and early 2000s, a few research papers connected to advanced propulsion studies began mentioning zero-point energy again. These papers did not claim that free energy devices existed. Instead, they asked whether quantum vacuum effects might influence inertia, gravity, or motion in ways that were not yet fully understood. The language was careful, technical, and often difficult to follow, but the ideas were enough to keep the mystery alive. One concept that appeared in some discussions was the possibility that inertia itself might be related to the vacuum. In everyday life, inertia is simply the tendency of an object to resist changes in motion. A heavy object is harder to move than a light one, and once something is moving, it takes effort to stop it. This seems like a basic rule of nature, something that does not need explanation. But some theoretical models suggested that inertia might come from interactions between matter and the quantum fields that fill space. If that were true, then the vacuum would not just be a background. It would be part of the reason objects have mass and resistance to motion in the first place. And if inertia depends on the vacuum, then in theory, changing the way an object interacts with the vacuum could change how it moves. Ideas like this are extremely speculative, and most of them never lead to practical results, but they show how deeply the concept of vacuum energy is connected to the foundations of physics. There were also studies about whether the vacuum could affect gravity. In Einstein's theory, gravity is not a force in the usual sense. It is the result of space-time bending around mass and energy. If the vacuum contains energy everywhere, then that energy should also affect the shape of space-time. In fact, modern cosmology already includes something like this. The expansion of the universe appears to be accelerating, as if space itself is being pushed outward by a kind of background energy. This effect is often called dark energy, and some theories suggest it could be related to zero-point energy. The connection is not fully understood, and many scientists think the two ideas are different, but the similarity is hard to ignore. Once again, the vacuum seems to be more than empty space. It becomes something active, something with real physical consequences, something that shapes the universe on the largest scales. Because NASA often works at the boundary between theory and engineering, some of these ideas naturally found their way into internal studies. Not because anyone expected to build a machine that runs on vacuum energy, but because understanding the vacuum might help explain things like propulsion efficiency, gravitational effects, or the behavior of matter in extreme conditions. When you design spacecraft that must survive in deep space, you sometimes end up asking questions that ordinary engineering never needs to ask. Over the years, a few of these research programs became known outside the scientific community, mostly because the topics sounded unusual. People heard phrases like advanced propulsion, quantum vacuum, or zero-point fields, and imagined that secret technology must be hiding behind the technical reports. In reality, most of the work was theoretical, exploratory, and often inconclusive. But the fact that serious institutions were willing to study these ideas at all was enough to keep the stories alive. There is something about the idea of hidden energy that captures the imagination. Maybe it is because energy is so important in everyday life. Everything we do depends on it, from electricity to transportation to communication. The thought that there might be an unlimited source of energy, quietly present everywhere, feels almost too good to be true. And most of the time, it probably is. Physics has a long history of showing that nature does not give away free power easily. Still, the vacuum remains one of the strangest parts of modern science. Even after decades of research, no one fully understands why it behaves the way it does. The equations work, the experiments agree with the predictions, but the deeper meaning is still unclear. Why does empty space have energy at all? Why does the universe allow fluctuations to exist even when nothing else is there? Why do the numbers come out so large in theory, yet so small in observation? Questions like that do not go away quickly. They stay in the background, waiting for new ideas, new experiments, or new technology that might reveal something unexpected. And as long as those questions remain, the possibility of hidden physics never completely disappears. So we keep going, slowly, step by step, deeper into the strange territory where quantum theory, space exploration, and the mysteries of the vacuum all begin to overlap. As the years went on, the idea of zero-point energy slowly moved from being a strange detail in quantum theory to something that appeared in conversations about the structure of the universe itself. Physicists working in different fields kept running into the same problem from different directions. Whenever the equations described empty space, they refused to give an answer of zero. There was always something left over, some tiny vibration, some background energy that could not be removed, no matter how carefully the math was done. This became especially important in cosmology, the branch of science that studies the universe on the largest scales. When scientists tried to understand why the universe exists in the form we see today, they found that the vacuum could not simply be ignored. The energy of empty space seemed to affect how space expands, how galaxies move, and even how the universe might end one day. Instead of being nothing, the vacuum started to look more like one of the most important ingredients in reality. One of the biggest surprises came when astronomers discovered that the expansion of the universe is accelerating. For a long time, scientists expected that gravity would slowly pull everything back together, or at least slow the expansion down over time. But careful observations showed the opposite. Distant galaxies were moving away faster than expected, as if something invisible was pushing space itself outward. The name given to this effect was dark energy, a term that sounds mysterious because no one really knows what it is. Some theories suggest that dark energy might be related to the same vacuum energy that appears in quantum physics. If empty space has energy, then that energy could act like a pressure, pushing space apart. The strange part is that the amount of dark energy observed in the universe is incredibly small compared to the amount predicted by quantum theory. Once again, the numbers do not match, and no one knows exactly why. But the connection keeps the idea alive that the vacuum is not just a passive background. It might be one of the most powerful things in existence. Whenever physics reaches a point where the equations do not fully agree with observation, researchers start looking for new ideas. Most of the time, those ideas stay within the limits of known science, but sometimes they go further. They explore possibilities that seem unlikely at first, simply because the current explanations are incomplete. This is how concepts like advanced propulsion, exotic energy systems, and unusual interactions with the vacuum occasionally appear in serious research, even if they never become mainstream. NASA has always had a practical reason to pay attention to these ideas. Space travel is limited by energy, mass, and distance. Chemical rockets work, but they are inefficient for long journeys. Nuclear propulsion could go further, but it comes with its own difficulties. If humanity ever wants to travel to other stars, the technology we use today will not be enough. Because of that, space agencies sometimes allow small research programs to explore concepts that sound far ahead of their time. These programs are usually quiet and very technical. They do not promise impossible machines. They do not claim that free energy is just around the corner. Instead, they ask careful questions about physics that is not fully understood yet. Could the vacuum influence inertia? Could space-time be manipulated in subtle ways? Could new propulsion methods exist that do not require carrying huge amounts of fuel? Most of the time the answer is no, but the questions are still worth asking, because space travel has always required thinking beyond what seems practical at first. In the late 20th century, a few theoretical studies looked at whether quantum vacuum effects could play a role in propulsion. The idea was not that a spacecraft could pull unlimited energy from empty space, but that the vacuum might interact with matter in ways that could create very small forces. If those forces could be understood, and if they could be controlled, then they might eventually lead to new kinds of engines, ones that do not work like rockets at all. One of the reasons this idea keeps coming back is that the Casimir effect already shows that the vacuum can produce a force. When two surfaces are placed extremely close together, the quantum fluctuations between them change, and the result is a measurable pressure. The effect is tiny, but it proves something important. It proves that empty space, can push on objects. And once that is proven, it becomes natural to wonder whether other vacuum effects might exist that are stronger or that behave differently under extreme conditions. Some researchers suggested that the vacuum might also be connected to inertia, the resistance objects have to changes in motion. In certain theoretical models, inertia comes from interactions between matter and the quantum fields that fill space. If this idea is correct, then the vacuum is not just sitting there quietly. It is constantly interacting with every particle, every atom, every object, all the time. Changing that interaction, even slightly, could in theory change how an object moves. These ideas are very difficult to test, and most of them remain purely theoretical. But they were interesting enough that a few small research efforts were funded to explore them. Some of those studies were connected to advanced propulsion concepts, the kind of work that does not usually make headlines because it is too uncertain, too experimental, and too far from practical engineering. When people later discovered references to these studies, the story started to grow. The fact that NASA had looked at vacuum energy, even in a theoretical way, was enough to spark speculation. Some people believed it meant secret technology already existed. Others thought it proved that free energy was being hidden. In reality, the truth was much less dramatic, but also more interesting. Scientists were simply trying to understand a part of physics that no one fully understands yet. The vacuum is one of those subjects that refuses to stay simple. Every time researchers think they have explained it, another question appears. Why does the vacuum have the energy it does? Why do the calculations give numbers that seem far too large? Why does the universe expand the way it does? Why do quantum fields behave the way they do even when no particles are present? Because these questions are still open, the subject never completely disappears. It stays in the background of physics, sometimes quiet, sometimes controversial, always a little mysterious. For people who like to imagine what might be possible in the future, zero-point energy becomes a symbol of hidden potential. Not proof that impossible machines exist, but a reminder that the universe is stranger than it looks. The laws of physics allow things that sound unbelievable at first, and history has shown that understanding those laws can lead to technologies no one expected. Electricity once seemed mysterious. Radio waves once sounded impossible. Space travel once belonged only in stories. Every generation has ideas that feel too far ahead to be real, until one day they are not. That is why the idea of vacuum energy keeps coming back, especially in conversations about space exploration, advanced physics, and the long-term future of technology. Not because anyone has built a device that runs on empty space, but because the science itself leaves the door slightly open, just enough to make people wonder. And as long as that door stays open, even a little, the stories will continue. Quiet research papers, forgotten experiments, strange effects that do not fit perfectly into the textbooks, and the constant feeling that the vacuum, the thing we call empty space, might still be hiding more than we understand. The deeper scientists looked into the nature of the vacuum, the more they realized that what we call empty space is actually one of the most complicated things in physics. In everyday life, we think of space as something simple, just the distance between objects, a background where everything else happens. But in modern physics, space is not just a container. It has structure, it has properties, and according to quantum theory, it is always active even when nothing seems to be there. One way to understand this is to imagine that space is filled with invisible fields that exist everywhere at once. These fields are not made of matter in the usual sense, but they can still carry energy and momentum. Particles appear when these fields vibrate in certain ways. And even when they are not vibrating enough to create particles, they still cannot become completely still. There is always a lowest level of motion, the 0-point level, and that motion means there is always some energy present. When physicists first discovered this, it felt like a strange technical detail, something that only mattered in very small experiments. But over time, the same idea kept showing up in larger and larger questions. It appeared in the behavior of atoms, in the theory of radiation, in the physics of black holes, and in the equations that describe the expansion of the universe. The vacuum was no longer just a place where things happen. It became something that could influence what happens. Because of this, the idea that the vacuum might contain enormous amounts of energy never completely went away. Even though most scientists believed that energy could not be extracted in any useful way, the fact that it existed in the equations kept the subject alive. Every few years, someone would ask the same question again. If space contains energy everywhere, why can we not use it? And every time, the answer would be complicated, because the rules of physics do not make it easy to take energy from a system that is already in its lowest possible state. In thermodynamics, energy can only be used when there is a difference, a change, a gradient between one state and another. A battery works because one side has more chemical energy than the other. A turbine works because water moves from high pressure to low pressure. Heat engines work because there is a difference in temperature. But the vacuum, at least in theory, is already at the lowest energy state allowed by the laws of physics. There is no obvious difference to exploit, no higher level to fall from, no simple way to make the energy flow. That is why most attempts to design so-called free energy devices fail. They assume the vacuum energy is like a hidden fuel waiting to be collected, but the physics suggests it is more like a perfectly balanced background, always present but not easy to disturb. Still, the fact that the background exists at all continues to make scientists curious, because the vacuum does not behave the way ordinary nothing should behave. In the world of advanced physics, curiosity often leads to careful experiments, even when the chances of success are small. NASA and other research organizations sometimes allow small projects to explore ideas that seem unusual, especially when those ideas might one day affect space travel. The distances involved in space exploration are so large that even a tiny improvement in propulsion or energy efficiency can make a huge difference. Because of that, researchers sometimes look at concepts that would sound unrealistic in other fields. During the late 20th century, a few theoretical studies examined whether the quantum vacuum might affect motion in ways that were not fully understood. These studies did not claim that spacecraft could run on zero-point energy, but they explored whether interactions between matter and the vacuum might produce very small forces. In normal conditions, those forces would be too weak to notice, but in extreme conditions, such as very strong electromagnetic fields or very small distances, the effects might become measurable. One idea that appeared in these discussions was that inertia itself might come from the vacuum. Normally, inertia is just the resistance an object has to being pushed or stopped. It feels like a basic property of matter, something that does not need explanation. But some theoretical models suggested that inertia could be the result of interactions between particles and the quantum fields that fill space. If that were true, then the vacuum would not just sit quietly in the background. It would be involved in every movement, every acceleration, every change of direction. If inertia depends on the vacuum, then in theory, changing the way an object interacts with the vacuum might change how it moves. This idea is extremely speculative, and most physicists think it will never lead to practical technology. But it is the kind of question that researchers sometimes explore simply to understand the laws of nature more deeply. Even if nothing useful comes from it, the process of studying the idea can reveal new information about how the universe works. Another reason these topics appear in advanced research is that the vacuum becomes especially important in extreme environments. Near black holes, inside particle accelerators, or in the very early universe, the energy of the vacuum may play a much larger role than it does in everyday life. NASA, because it studies space, often deals with conditions that are far more extreme than anything on Earth. Understanding the vacuum is not just a philosophical question. It can affect how instruments behave, how radiation moves, and how matter interacts with space itself. Because of that, small references to vacuum energy sometimes appear in technical reports about advanced propulsion, exotic physics, or experimental theories. These reports are usually cautious and very technical, but when people outside the scientific community read them, the language can sound mysterious. Words like quantum vacuum, zero-point field, or space-time energy naturally make the imagination start to wander. Over time, this has created a kind of legend around the subject. Every time someone hears that NASA studied vacuum energy, the story grows a little. Some people imagine secret engines hidden in laboratories. Others believe that new energy sources already exist but are not being released. In reality, most of the research is simply scientists trying to understand a very strange part of physics, one that no one has fully explained yet. The truth is that modern science still does not know why the vacuum has the energy it does. The equations of quantum field theory predict enormous values, far larger than anything we observe in the universe. Cosmology suggests there is some form of vacuum energy affecting the expansion of space, but its size is much smaller than the theory predicts. This mismatch is one of the biggest unsolved problems in physics, and it means our understanding is incomplete. Whenever understanding is incomplete, the possibility of new discoveries remains. Not necessarily discoveries that break the laws of physics, but discoveries that show the laws are more complicated than we thought. History has shown that this happens again and again. When scientists learn more about nature, the picture usually becomes deeper, not simpler. That is why the idea of zero-point energy continues to appear in discussions about the future. Not as proof of unlimited power, but as a reminder that the universe is still full of questions. Empty space is not really empty. Motion never completely stops. Energy never fully disappears. And somewhere inside those facts, there may still be things we have not learned yet. By the time physicists reached the end of the 20th century, the vacuum had become one of the most puzzling ideas in all of science. What once sounded like a simple concept had turned into something almost impossible to describe in ordinary language. Empty space was no longer empty. It had energy, structure, and behavior that could only be explained with mathematics so complex that even experts sometimes disagreed about what the equations really meant. One of the reasons the subject became so confusing is that there are actually several different kinds of vacuum in physics. In everyday life, a vacuum simply means removing air from a container. In classical physics, it means a region with no matter and no radiation. But in quantum physics, the vacuum is the lowest energy state of all the fields that exist in space, and that state still contains motion. Even when everything that can be removed has been removed, the fields remain, and they continue to fluctuate. These fluctuations are not random in the way ordinary noise is random. They follow precise mathematical rules. Particles can appear and disappear in pairs, borrowing energy from the vacuum for a tiny fraction of a second, then giving it back before the laws of physics are violated. This strange behavior is allowed because of the uncertainty principle, which says that energy and time cannot both be known exactly at the same moment. For very short times, the universe allows small amounts of energy to appear, as long as they disappear again quickly. At first, this idea sounded like a trick of the equations, something that only existed on paper. But experiments kept showing that the effects were real. The Casimir effect, which produces a tiny force between very close surfaces, could be measured in laboratories. Small shifts in atomic energy levels could be explained by interactions with vacuum fluctuations. Even the behavior of certain particles in accelerators seemed to depend on the energy of empty space. Because of results like these, scientists stopped thinking of the vacuum as nothing. Instead, they began to think of it as the lowest level of something very complicated, a kind of restless background that never becomes completely still. And once the vacuum started to look active, the idea that it might have hidden properties became harder to dismiss. This is one of the reasons the concept of zero-point energy continued to appear in discussions about advanced physics, especially in areas connected to space research. NASA and similar organizations sometimes study ideas that are not immediately useful, simply because understanding the fundamentals of physics can eventually lead to new technology. When you are working on spacecraft, satellites, and long-distance missions, even small improvements in efficiency can matter. So it makes sense to explore theories that might one day change how we think about energy or motion. In the 1990s, a small number of research papers looked at whether the quantum vacuum might influence inertia or propulsion in subtle ways. These papers did not claim that free energy machines existed. They were careful, theoretical studies, asking whether the interaction between matter and the vacuum could produce effects that had not yet been fully understood. Some of the ideas were extremely speculative, but they were still considered worth examining because the physics of the vacuum was not completely settled. One of the more unusual suggestions was that inertia might come from the resistance of the vacuum itself. Normally, inertia is just taken as a basic fact. Objects resist changes in motion, and that is the end of the story. But some theoretical models propose that when an object accelerates, it interacts with the quantum fields that fill space, and those interactions create the force we experience as inertia. In this view, the vacuum is not passive. It pushes back whenever something tries to move. If that idea were correct, then in theory, changing the interaction between matter and the vacuum could change the way inertia behaves. The effect would probably be extremely small, and no one has ever demonstrated it in a practical way, but the possibility was interesting enough that a few researchers explored it further. These studies stayed mostly inside academic journals and technical reports, but they added to the growing sense that the vacuum might be more important than anyone once thought. Another area where vacuum energy appeared was in attempts to understand gravity at the quantum level. Einstein's theory of gravity describes how mass and energy bend space-time, but it does not explain how gravity fits with quantum mechanics. When physicists try to combine the two theories, the vacuum becomes impossible to ignore. The energy of empty space should affect gravity, but the predicted amount is far larger than what we observe in the universe. This mismatch is still one of the biggest unsolved problems in physics. Some researchers suggested that the answer might involve new physics that has not been discovered yet. Others thought the vacuum energy might cancel itself out in ways we do not fully understand. And a few wondered whether the vacuum might behave differently under extreme conditions, such as very strong fields or very small distances. Ideas like these are difficult to test, but they keep the subject open because the current theories do not give a complete explanation. Whenever science reaches that kind of uncertainty, imagination naturally fills the gap. People begin to wonder what might be possible if the missing pieces were found. If the vacuum contains energy, could it ever be used? If inertia depends on the vacuum, could it be altered? If gravity is connected to vacuum fields, could space itself be manipulated? Most scientists are cautious about questions like these, but they are still asked because history has shown that some of the strangest ideas eventually lead to real discoveries. For space agencies, the motivation is practical as well as theoretical. Traveling through space is difficult, expensive, and slow. Even the fastest spacecraft we have built would take thousands of years to reach the nearest stars. Because of that, researchers sometimes look at concepts that seem far beyond current technology, not because they expect immediate results, but because the future of exploration may depend on ideas that sound impossible today. This is why small studies into advanced propulsion, quantum effects, and unusual energy systems occasionally appear in official research programs. Most of them never lead to working devices. Many are eventually abandoned. But a few produce useful insights, and those insights slowly become part of the larger understanding of physics. The idea of zero-point energy fits into this pattern perfectly. It is not a proven energy source. It is not a hidden machine waiting to be turned on. It is a strange property of the universe that no one fully understands yet. And because it is not fully understood, it leaves room for questions, for speculation, and for the quiet feeling that reality may still hold surprises. As we keep drifting deeper into this subject, the story becomes less about secret technology and more about the nature of the universe itself. The vacuum is not empty. Motion never fully stops. Energy never completely disappears. And somewhere in those facts, there may still be pieces of physics that have not been discovered yet. We will keep following that trail. As the research into vacuum physics continued, scientists slowly became used to the idea that the universe is never completely quiet. Even in the deepest emptiness, even in the coldest possible conditions, something is always happening. Tiny fluctuations move through the quantum fields, energy shifts appear and disappear, and space itself seems to behave less like an empty stage and more like a living background that never fully rests. This picture of reality is very different from the one people imagined 100 years ago, and it is one of the reasons the subject of zero-point energy keeps returning in conversations about advanced science. One of the most interesting things about the vacuum is that its effects are usually extremely small, but the equations behind those effects often suggest something much larger hiding underneath. In laboratory experiments, vacuum fluctuations produce only tiny forces, tiny shifts, tiny corrections to measurements. But when the same mathematics is extended to the scale of the entire universe, the predicted energy becomes enormous. It is as if the background of space contains far more energy than we can see, but most of it is locked away in a perfectly balanced state. Physicists sometimes describe this as the difference between what is allowed by theory and what is possible in practice. The equations of quantum field theory allow the vacuum to contain huge amounts of energy, but the laws of thermodynamics make it extremely difficult to use that energy for anything useful. It is similar to having an ocean of water around you, but no easy way to turn that water into electricity without a difference in height or pressure. The energy is there, but it is not available in a form you can easily take. Still, the idea that space itself holds energy has never stopped being fascinating, especially for people working in fields where energy and motion are constant challenges. In space exploration, every kilogram of fuel matters. Every increase in efficiency matters. Even a small improvement in propulsion can change what missions are possible. Because of that, researchers sometimes look at theories that seem unusual, simply because the reward would be so large if any part of them turned out to be true. NASA has always had small programs that explore advanced concepts, not because they expect immediate success, but because long-term progress often comes from ideas that once sounded unrealistic. Some of these studies involve new materials, some involve new propulsion systems, and some involve fundamental physics that is not fully understood yet. The quantum vacuum appears in these discussions from time to time, usually in a very cautious way, as scientists try to understand whether its properties could ever have practical effects. In the late 20th century, a few theoretical investigations looked at whether interactions with the vacuum might influence inertia, gravity, or electromagnetic forces. These studies did not claim that the vacuum could be used as a power source, but they asked whether the background energy of space might affect the way objects move. If inertia depends on interactions with quantum fields, then the vacuum is involved in every motion, every acceleration, every force, even if we normally do not notice it. One idea that appeared in some papers suggested that when an object accelerates, it may experience resistance because of how it interacts with the vacuum fields around it. This resistance would show up as inertia, the same effect we feel whenever we try to push something heavy. In this view, Inertia is not just a property of matter, but a result of how matter interacts with the quantum structure of space itself. The theory is difficult to test, and most physicists remain skeptical, but it shows how deeply the vacuum may be connected to the basic laws of motion. There were also discussions about whether the vacuum could affect gravity in ways that are not yet fully understood. In Einstein's theory, gravity comes from the curvature of space-time caused by mass and energy. If the vacuum contains energy everywhere, then it should also contribute to that curvature. In fact, modern cosmology already includes something like this, in the form of dark energy, the mysterious effect that seems to be pushing the universe to expand faster and faster. The connection between dark energy and zero-point energy is not clear, but the similarity keeps scientists interested. Both ideas suggest that empty space has properties that are not obvious. Both suggest that the vacuum is not just nothing. And both remind us that the universe may still contain physics that has not been fully discovered yet. Because NASA often works at the edge of what is known, it sometimes becomes connected to these discussions. When researchers study advanced propulsion, they sometimes ask whether space itself could be part of the solution. Not because anyone expects to build a machine that runs on vacuum energy tomorrow, but because understanding the vacuum might reveal small effects that could eventually matter in extreme conditions. For example, some theoretical propulsion concepts look at whether electromagnetic fields could interact with space-time in ways that produce thrust without using traditional fuel. These ideas are highly speculative, and most of them remain purely mathematical. But they are studied carefully because space travel has always required thinking beyond what seems practical at first. Even the idea of leaving Earth once sounded impossible, and yet it became reality through decades of slow, careful work. Over the years, stories about these studies have grown in ways that the scientists themselves never intended. When technical reports mention quantum vacuum effects, the language can sound mysterious to anyone outside the field. Words like zero-point field, space-time energy, or vacuum fluctuations naturally make people imagine hidden technology or secret experiments. In reality, most of the research is simply an attempt to understand the universe more deeply, not to build impossible machines. Still, the mystery remains because the physics itself is not finished. No one fully understands why the vacuum has the energy it does. No one knows why the theoretical predictions are so much larger than what we observe. No one has a complete theory that combines quantum mechanics, gravity, and cosmology into one clear picture. Until those questions are answered, the subject of vacuum energy will always feel a little open, a little unfinished. And when a subject feels unfinished, it invites imagination. It invites the thought that maybe there is more to discover, more to understand, more to learn about the structure of reality itself, not because the laws of physics are wrong, but because they may not yet be complete. So the story of zero-point energy continues quietly in the background of science, not as proof of hidden power, but as a reminder that the universe is more complicated than it looks. Space is not empty. Motion never fully stops. Energy never disappears completely. And somewhere inside those facts, there may still be ideas waiting to be understood. As physicists continued to explore the strange behavior of the vacuum, one thing became clear. The deeper the theory went, the less the universe looked like a collection of solid objects moving through empty space. Instead, reality started to look more like a network of invisible fields, constantly interacting, constantly vibrating, even when nothing seems to be happening. Matter, energy, and even space itself appeared to be different expressions of the same underlying structure. This way of thinking changed how scientists approached some of the biggest questions in physics. If the vacuum is not empty, then it might play a role in processes that were once thought to depend only on matter. If space contains energy, then that energy might influence motion, gravity, and the behavior of particles in ways that are very difficult to see under normal conditions. Most of the time, these effects are too small to notice, but in extreme environments, they might become more important. One place where the vacuum becomes especially important is near very strong electromagnetic fields. In ordinary situations, the fluctuations of the vacuum cancel each other out so perfectly that no usable energy appears. But when fields become extremely intense, the balance can shift slightly. Under those conditions, the vacuum itself can behave differently, almost as if it becomes a kind of medium rather than empty space. Experiments with high-energy lasers and particle accelerators have shown hints of this behavior, although the effects are very small and very difficult to measure. Because space research often deals with extreme conditions, these ideas sometimes appear in studies connected to advanced propulsion or high-energy physics. NASA and other agencies occasionally fund theoretical work that asks what might happen if the known laws of physics are pushed to their limits. These studies do not promise impossible technology, but they explore the edges of what the equations allow, looking for effects that might one day become useful. One of the reasons this kind of research continues is that history has shown that new technology often comes from unexpected places. When electricity was first studied, no one imagined global communication networks. When radio waves were discovered, no one expected satellites. When quantum mechanics was first developed, no one predicted computers built from microscopic circuits. Because of that, scientists sometimes investigate ideas that seem impractical, simply to understand what nature allows. The vacuum is one of those ideas that never quite settles into a simple explanation. Every time physicists think they understand it, another question appears. Why does the vacuum have the energy it does? Why do quantum fields fluctuate even when there are no particles? Why does the expansion of the universe seem to depend on a form of energy that no one can see directly? These questions do not have complete answers yet, and because of that, the subject always feels a little mysterious. In some theoretical models, the vacuum is not just a background but the foundation of everything. Instead of particles being the most basic things in nature, the fields that fill space might be the true starting point. Particles would then be small excitations of those fields, like waves on the surface of an ocean. If that picture is correct, then the vacuum is not nothing at all. It is the lowest state of the entire universe, the quietest level of a system that never fully stops moving. Thinking about space this way can make the idea of hidden energy feel less impossible, even if it is still not practical. The energy is not hidden in the sense of being stored somewhere waiting to be taken. It is hidden because it exists everywhere at once, balanced so perfectly that there is no easy way to separate it from the rest of reality. It is like trying to take motion out of the ocean without disturbing the water. The motion is everywhere, but it does not collect in one place. Still, the fact that the vacuum can produce real effects keeps scientists interested. The Casimir force is one example, but there are others. Small shifts in atomic energy levels, known as the Lamb shift, can be explained by interactions with vacuum fluctuations. Certain particle processes only make sense when the energy of empty space is included in the calculations. Even the radiation predicted to come from black holes, called Hawking radiation, depends on the idea that the vacuum is full of temporary particle pairs appearing and disappearing. These effects are not science fiction. They are part of accepted physics. But they also show how strange the universe really is. Something as simple as empty space turns out to be one of the most complicated things scientists have ever tried to understand. Because of this, the subject sometimes overlaps with more speculative ideas, especially when people start thinking about the long-term future of space travel. If humanity ever wants to travel far beyond the solar system, new forms of propulsion will be needed. Carrying fuel for thousands of years is not practical. Generating energy along the way would be far more efficient. but the known sources of energy all have limits. That is why some researchers occasionally look at concepts that involve the structure of space itself. Most of these ideas remain theoretical, and many will probably never lead to real technology. But studying them can still teach us something about physics. Even if zero-point energy never becomes a power source, understanding why it cannot be used might reveal deeper laws of nature. Sometimes learning what is impossible is just as important as learning what is possible. NASA's involvement in these topics has always been cautious. The agency studies many ideas that never become public knowledge, simply because they are part of long-term research. Some projects last only a few years. Some produce results that are interesting but not useful. Others raise new questions that lead to more studies later. From the outside, it can look mysterious, but from the inside, it is just the normal process of science moving slowly forward. Still, the idea of energy hidden in empty space continues to capture the imagination. It feels like one of those concepts that belongs halfway between science and mystery. The equations say the energy is there. Experiments show that the vacuum is active. Cosmology suggests that empty space affects the entire universe, yet no one has found a way to turn that knowledge into unlimited power, and no one knows if that will ever happen. That uncertainty is part of what makes the subject so interesting. The vacuum is real, the energy is real, the effects are real, but the full meaning is still unknown. Somewhere between what we understand and what we have not discovered yet, the idea of zero-point energy continues to exist, quiet, invisible, and impossible to completely ignore. As research into the vacuum continued, scientists slowly became aware of something that made the subject even more puzzling. The energy of empty space was not just a strange detail in quantum theory. It seemed to appear everywhere, in almost every attempt to describe the universe at its most fundamental level. Whether physicists were studying atoms, black holes, or the expansion of the cosmos, the vacuum kept showing up in the equations, always present, always impossible to remove completely. One of the reasons this idea feels so unusual is because our everyday experience tells us the opposite. When we think of nothing, we imagine silence, darkness, stillness, the absence of everything. But in modern physics, nothing is never truly nothing. Even the most perfect vacuum imaginable still contains fields, fluctuations, and energy that cannot be turned off. It is a kind of background activity built into the structure of reality itself. In quantum field theory, the vacuum is the lowest possible energy state, but it is not zero. Every field that exists in space has a minimum level of vibration that cannot be removed. This vibration is extremely small, but when the equations add up all the fields together, the total energy becomes very large. So large, in fact, that it creates one of the biggest mysteries in physics. The predicted vacuum energy is far greater than anything we observe in the real universe. This problem has been studied for decades, and no one has found a simple explanation. Some physicists think the energy must cancel itself out through a mechanism that has not been discovered yet. Others believe our understanding of the vacuum is incomplete. A few even suggest that the energy might be real, but hidden in a way we do not yet know how to measure. Whatever the answer turns out to be, it means that empty space is still one of the least understood parts of modern science. Because the vacuum appears in so many different theories, it naturally becomes part of discussions about the future of physics. When scientists try to imagine new ways to travel through space, new ways to generate energy, or new ways to understand gravity, the vacuum often becomes part of the conversation. Not because anyone has found a way to use it directly, but because it seems to be connected to the deepest layers of reality. NASA, like many research organizations, sometimes studies ideas that are far ahead of current technology. These studies are usually small and very theoretical, but they are allowed to exist because space exploration has always depended on new ideas. If the only research that was done were the kind that already works, nothing new would ever be discovered. So from time to time, scientists look at concepts that seem unlikely, simply to see where the limits of physics really are. In some of these studies, the quantum vacuum appears as a possible factor in advanced propulsion. The idea is not that a spacecraft could run on zero-point energy like a battery. Instead, the question is whether the interaction between matter and the vacuum could produce effects that change how motion works. If inertia or gravity depends on the vacuum, then understanding that connection might lead to new ways of moving through space, even if the effect is very small. One example that has been discussed in theoretical papers is the possibility that the vacuum contributes to inertia. In normal physics, inertia is just a property of mass. The more mass something has, the harder it is to accelerate. But some models suggest that when an object accelerates, it interacts with the quantum fields that fill space, and that interaction produces resistance. In this picture, inertia is not just inside the object. It comes from the object's relationship with the vacuum. If this idea were correct, then the vacuum would be involved in every movement in the universe. Every time something speeds up or slows down, it would be interacting with the background fields of space itself. Changing that interaction would not be easy, and no one has ever demonstrated a way to do it. But the idea is interesting because it connects motion to the structure of the vacuum. Another place where the vacuum becomes important is in the study of black holes. According to modern physics, black holes are not completely black. They can slowly lose energy through a process called Hawking radiation. This radiation comes from the behavior of the vacuum near the edge of the black hole. Quantum fluctuations can create pairs of particles, and under certain conditions, one of those particles can escape while the other falls in. The result is a tiny flow of energy coming from what looks like empty space. This effect is extremely small for ordinary black holes, but it shows something remarkable. It shows that the vacuum is not just a passive background. Under the right conditions, it can produce real energy that can be measured. The laws of physics still hold, and no energy is created from nothing, but the process depends on the strange behavior of the vacuum fields that exist everywhere. Cosmology gives another example. The expansion of the universe appears to be speeding up, and the simplest explanation involves a form of energy that exists even in empty space. This energy, often called dark energy, may be related to the same vacuum energy predicted by quantum theory. The connection is not fully understood, but the similarity keeps scientists interested, because it suggests that the vacuum might influence the universe on the largest possible scale. When people outside the scientific community hear about ideas like this, the imagination naturally takes over. If empty space contains energy, it sounds like there should be a way to use it. If the vacuum affects gravity, it sounds like space could be controlled. If quantum fields exist everywhere, it sounds like hidden forces might be waiting to be discovered. These thoughts are understandable, but the reality is usually more complicated. The laws of physics make it very difficult to turn these ideas into practical technology. Still, the fact that the vacuum is so mysterious means the subject never fully goes away. Even among scientists, there is a feeling that the current theories are not complete. Quantum mechanics and gravity still do not fit together perfectly. The predicted energy of the vacuum does not match observation. The origin of dark energy is unknown. Questions like these leave room for new discoveries, even if those discoveries turn out to be very different from what people imagine. For NASA and other research groups, this means the vacuum remains worth studying, even if the results are uncertain. Understanding the nature of space itself could one day affect propulsion, energy, or the way we explore the universe. Not because there is a secret power source waiting to be turned on, but because the laws of nature may still have details we have not learned yet. And that is what keeps the idea of zero-point energy alive. Not proof of hidden technology, not evidence of impossible machines, but a reminder that the universe is stranger than it looks. Empty space is not empty. Motion never fully stops. Energy never completely disappears. And somewhere in those facts, there may still be discoveries waiting quietly in the background, just beyond what we understand today. As the understanding of quantum physics grew more detailed, scientists began to notice that the vacuum was not only strange, but also unavoidable. Every time they tried to describe the universe without including the energy of empty space, the equations stopped working. It did not matter whether the subject was particle physics, cosmology, or gravity. The vacuum always returned, like a background that could never be removed from the picture. One of the reasons this happens is because quantum theory does not allow complete stillness. In classical physics, you can imagine a system with no motion at all, perfectly at rest. But in quantum mechanics, that state is impossible. The uncertainty principle requires that there is always some fluctuation, some tiny movement that cannot be eliminated. Even if the energy is extremely small, it must exist. That unavoidable motion becomes the zero-point energy, the lowest level that the universe allows. When scientists calculate the total energy of the vacuum using quantum field theory, the result is enormous. Every field contributes a small amount, but there are many fields, and when the contributions are added together, the number becomes almost unbelievable. If the calculation were taken literally, the energy in empty space would be enough to overpower gravity and tear the universe apart. Yet the real universe does not behave that way. Galaxies exist, stars exist, and the expansion of space is much slower than the equations predict. This difference between theory and observation is one of the greatest puzzles in modern physics. It suggests that something important is missing from our understanding. Either the calculations are incomplete, or there is some unknown process that cancels most of the vacuum energy out. Until that problem is solved, the vacuum remains one of the biggest mysteries scientists have ever faced. Because of this mystery, the vacuum sometimes becomes part of research into very advanced ideas. When scientists do not fully understand something, they often explore many possibilities, even ones that seem unlikely at first. Most of these ideas never lead to practical results, but a few help reveal new pieces of the puzzle. NASA and other research organizations occasionally support this kind of work, especially when it might affect space travel or fundamental physics. Space exploration has always required thinking beyond what seems normal. The distances are too large, the energy requirements too high, and the conditions too extreme for ordinary engineering to be enough. Because of that, some researchers look at concepts that involve the structure of space itself. They ask whether the vacuum might influence motion, whether space-time could behave differently under certain conditions, or whether unknown effects might appear when fields become very strong. These questions do not mean that secret technology already exists. Most of the time, the answers show that the limits of physics are exactly where we thought they were. But the process of asking the question can still be valuable, because it forces scientists to examine the foundations of their theories. Sometimes the result is simply a better understanding of why something cannot be done. Other times, the result is a small discovery that leads to new ideas later. One area where the vacuum becomes especially important is in the study of extreme energy fields. In ordinary life, vacuum fluctuations are too small to notice. But when electromagnetic fields become very strong, the behavior of the vacuum can change slightly. In high-energy experiments, scientists have observed effects that suggest empty space can act almost like a material under certain conditions. Light passing through strong fields can behave differently, as if the vacuum itself has properties that only appear when the energy is high enough. These effects are very subtle, and they do not produce unlimited energy or anything close to it, but they show that the vacuum is not as simple as it looks. It can respond to energy, it can influence particles, and it can behave differently depending on the conditions. Because of that, some theoretical studies have asked whether the vacuum might play a role in propulsion systems that work very differently from rockets. Traditional rockets move by pushing mass in one direction to move the spacecraft in the other. This method works well for short distances, but it becomes inefficient for long journeys. Carrying enough fuel to travel between stars would make a spacecraft far too heavy to launch. Because of this, scientists sometimes look at ideas that do not require carrying large amounts of fuel. These ideas are usually theoretical, and many will never become practical, but they are studied because the reward would be enormous if even one of them worked. Some of these studies have examined whether interactions with the vacuum could produce very small forces that might be used for propulsion. The idea is not to pull energy out of empty space, but to use the properties of space itself to create motion. In theory, if the vacuum affects inertia or electromagnetic fields, then under certain conditions it might be possible to produce thrust without throwing mass backward. So far, no experiment has shown a clear way to do this, but the idea continues to appear in theoretical discussions. Another reason the vacuum attracts attention is its connection to cosmology. The expansion of the universe suggests that space contains some form of energy, even when no matter is present. This energy seems to act like a pressure that pushes space apart. Some scientists believe this effect may be related to zero-point energy, although the exact relationship is still unknown. If that connection is real, then the vacuum is not only important for small-scale physics, but also for the fate of the entire universe. Because these questions are still open, the subject of vacuum energy never fully disappears. It moves in and out of the spotlight, sometimes ignored, sometimes studied again when new theories appear. Each time it returns, the story sounds a little mysterious, because the idea itself is difficult to explain without sounding like science fiction. Energy in empty space, particles appearing from nothing, forces that exist without visible cause. These are real concepts in physics, but they do not match the way we normally think about the world. Over time, this has created a strange mixture of science and speculation. Serious researchers study the vacuum because the equations require it. Others imagine what might happen if the hidden energy of space could be used. Most of those ideas never lead to real technology, but the possibility always feels like it is just far enough away to keep people curious. For NASA, the interest in the vacuum has always been practical as well as theoretical. Understanding space itself is part of understanding how to travel through it. Even if zero-point energy never becomes a power source, the physics behind it may still affect how spacecraft move, how radiation behaves, or how gravity works on very large scales. Because of that, the subject remains worth studying, even if the answers come slowly. And so the idea continues quietly in the background of modern physics. The vacuum is not empty. Energy never fully disappears. Motion never completely stops. And somewhere inside those facts, there may still be pieces of the universe we have not learned how to see yet. The more scientists tried to understand the vacuum, the more they realized that the problem was not just about energy. It was about the nature of reality itself. The idea that empty space could contain energy forced physicists to rethink some of their most basic assumptions. Instead of seeing the universe as objects moving through nothing, they began to see it as patterns moving through something that is always there, even when it cannot be seen directly. One of the strange consequences of quantum theory is that the vacuum is never truly stable. Even in its lowest possible energy state, it is constantly fluctuating. Tiny changes happen everywhere at once, too small to notice individually, but always present. These fluctuations are not mistakes in the math. They are required by the uncertainty principle, one of the most fundamental rules in physics. According to that rule, certain quantities can never be known exactly at the same time, and that uncertainty means the universe can never be perfectly still. This idea becomes even more interesting when physicists think about the early universe. Right after the beginning of the cosmos, conditions were so extreme that the energy of the vacuum may have played a much larger role than it does today. Some theories suggest that the rapid expansion in the first moments after the Big Bang was driven by vacuum energy, causing space itself to stretch faster than anything could move through it. If that is true, then the vacuum was not just present at the beginning of the universe. It may have helped shape the entire structure we see now. Cosmology also suggests that something similar might still be happening. The expansion of the universe is accelerating, as if space itself contains a kind of pressure that pushes everything apart. Scientists call this dark energy because its origin is unknown. Some theories connect dark energy to the same vacuum energy predicted by quantum physics, but the numbers do not match. The predicted energy is far too large, and no one knows why the real universe seems to use only a tiny fraction of it. This mismatch keeps the subject open because it shows that our current theories are incomplete. When physics reaches a point where the equations work, but the meaning is unclear, researchers start looking for new ideas. Most of those ideas stay within the limits of known science, but some explore possibilities that sound unusual. Not because scientists believe in impossible machines, but because understanding the vacuum may require thinking in ways that feel unfamiliar. NASA has occasionally been involved in studies like this, not because the agency expects to find unlimited energy, but because space exploration often depends on understanding physics at a deeper level. When engineers design spacecraft, they must deal with radiation, gravity, extreme temperatures, and environments far beyond anything on Earth. Sometimes the questions that come up lead into areas of theory that are still being explored, including the behavior of the vacuum. In the late 20th and early 21st centuries, a few small research programs looked at advanced propulsion concepts that involved quantum effects. These studies were cautious and theoretical, asking whether the vacuum might influence motion in ways that had not yet been tested. Some papers discussed whether electromagnetic fields could interact with space-time differently under certain conditions. Others examined whether inertia might be connected to the quantum fields that fill space. These ideas did not lead to working engines, but they showed how the vacuum could appear in unexpected places. If inertia comes from interactions with the vacuum, then every movement depends on space itself. If gravity is connected to vacuum energy, then the structure of the universe depends on the properties of empty space. If quantum fluctuations exist everywhere, then the background of reality is never truly quiet. Because of ideas like these, the vacuum sometimes feels less like nothing and more like a hidden layer of the universe, something we cannot see directly but cannot remove from the equations. This does not mean there is secret technology waiting to be discovered, but it does mean the laws of physics may still have details we have not learned yet. Another reason the subject remains interesting is that the vacuum becomes important in extreme environments. Near black holes, for example, quantum fluctuations can create real particles. According to the theory of Hawking radiation, the vacuum near the edge of a black hole behaves differently because of the intense gravity. Particle pairs can form, and one of the particles can escape while the other falls in. The result is a tiny flow of energy coming from what looks like empty space. This effect is extremely small, but it shows that the vacuum can produce real energy under the right conditions. The laws of physics are not broken because the energy comes from the gravitational field, but the process depends on the strange behavior of the vacuum itself. Situations like this remind scientists that empty space is not simple, and that its properties can change when the environment becomes extreme enough. Experiments with very strong electromagnetic fields also suggest that the vacuum can behave differently when energy levels are high. In certain conditions, empty space can act almost like a material, affecting the way light moves through it. These effects are difficult to observe, but they match the predictions of quantum theory. Once again, the vacuum shows that it has structure, even if that structure is normally invisible. Because space exploration often involves extreme conditions, NASA researchers sometimes pay attention to these ideas. Not because they expect to find a way to power spacecraft with zero-point energy, but because understanding the vacuum could affect how instruments work, how radiation behaves, or how propulsion systems perform in unusual environments. Even small effects can matter when missions travel far from Earth. Over time, stories about these studies have grown into something more mysterious than the science itself. When people hear that vacuum energy appears in NASA research, it sounds like proof that hidden technology must exist. In reality, the work is usually theoretical, careful, and uncertain. Scientists are trying to understand the rules of nature, not break them. Still, the mystery remains because the vacuum is not fully understood. The predicted energy is too large. The observed energy is too small. Quantum mechanics and gravity still do not fit together perfectly. And until those problems are solved, the subject of zero-point energy will always feel unfinished. That unfinished feeling is what keeps the idea alive. Not as evidence of secret machines, but as a reminder that science is still learning. The universe is deeper than it looks. Empty space is not empty. Motion never fully stops. Energy never disappears completely. And somewhere in those facts, there may still be discoveries waiting, quiet and hidden, inside the structure of space itself. As the study of the vacuum continued into the modern era, physicists became more and more certain about one thing, even if many other things remained uncertain. Empty space is not nothing. It has measurable effects, it influences particles, and it appears in almost every theory that tries to describe the universe at its deepest level. What scientists still do not know is why the vacuum has the properties it does, or why its energy seems so different in theory compared to what we observe in reality. This difference between prediction and observation has become one of the most famous problems in physics. When quantum field theory calculates the energy of the vacuum, the number comes out incredibly large. When cosmology measures the energy that seems to be pushing the universe apart, the number is very small by comparison. Both results appear to be correct in their own context, but they do not agree with each other. Somewhere in between, something is missing from the picture. Whenever science reaches that kind of gap, researchers begin to explore new ideas. Some of those ideas stay close to existing theories, adjusting equations, and looking for hidden cancellations that might explain the difference. Others go further, asking whether the vacuum might behave differently under conditions we have never been able to test. These questions do not mean that scientists believe the laws of physics are wrong. They mean the laws may not yet be complete. Because the vacuum appears in so many areas of physics, it naturally becomes part of research connected to the future of space exploration. NASA and other agencies often look at long-term possibilities, even when the technology does not exist yet. If humanity ever wants to travel beyond the solar system, new methods of propulsion will almost certainly be needed. Chemical rockets are powerful, but they are inefficient for very long distances. Nuclear propulsion could help, but even that has limits. Because of this, scientists sometimes examine ideas that involve the structure of space itself. In a few theoretical studies, the quantum vacuum has been considered as part of advanced propulsion concepts. These studies are usually very cautious. They do not claim that energy can be pulled from empty space, and they do not suggest that free power is waiting to be discovered. Instead, they ask whether the interaction between matter and the vacuum might produce effects that could change the way motion works, especially in extreme conditions. One idea that appears from time to time is that the vacuum might be connected to inertia. In everyday life, inertia is simply the resistance an object has to changes in motion. A heavy object is harder to move than a light one, and once something is moving, it takes effort to stop it. This seems like a basic rule of nature, but some theoretical models suggest that inertia might come from interactions between matter and the quantum fields that fill space. If that idea is correct, then every movement in the universe involves the vacuum in some way. When an object accelerates, it may be interacting with the background fields that exist everywhere. The resistance we feel as inertia could come from those interactions rather than from the object alone. No experiment has proven this in a practical sense, and most physicists consider the idea speculative, but it shows how deeply the vacuum may be connected to the laws of motion. There have also been discussions about whether the vacuum might influence gravity. In Einstein's theory, gravity comes from the curvature of space-time caused by mass and energy. If the vacuum contains energy everywhere, then it should also affect that curvature. In fact, modern cosmology already includes something similar in the form of dark energy, the mysterious effect that appears to be accelerating the expansion of the universe. Some scientists think dark energy might be related to zero-point energy, while others believe it comes from something completely different. The problem is that the numbers predicted by quantum theory are far larger than what we observe. If the vacuum really contained as much energy as the equations suggest, the universe would look very different. Understanding why it does not is one of the biggest challenges in modern physics. Because of these unanswered questions, the vacuum remains a subject that scientists continue to study, even when the results are uncertain. Research into advanced physics often includes ideas that sound unusual, not because anyone expects them to work immediately, but because the limits of nature are not fully known. NASA has occasionally supported this kind of research, especially when it might relate to propulsion, energy, or the behavior of matter in extreme environments. From the outside, these studies can sound mysterious. When people hear phrases like quantum vacuum, zero-point field, or advanced propulsion, it is easy to imagine hidden technology or secret experiments. In reality, most of the work is theoretical, careful, and often inconclusive. Scientists are trying to understand how the universe works, not trying to hide impossible machines. Still, the subject keeps its sense of mystery because the physics itself is not finished. The vacuum cannot be removed from the equations, but it also cannot be fully explained. It has energy, but that energy cannot easily be used. It affects the universe, but its exact role is still unknown. Every time researchers think they are close to understanding it, another question appears. Black holes give one example of how strange the vacuum can be. According to modern theory, the empty space near the edge of a black hole behaves differently from the vacuum far away. Quantum fluctuations can create particle pairs, and gravity can separate them before they disappear. One particle escapes, and the other falls into the black hole. The result is a tiny amount of energy leaving the black hole, a process known as Hawking radiation. It is extremely small, but it shows that the vacuum can produce real effects when the conditions are extreme. High-energy experiments show something similar. When electromagnetic fields become strong enough, the vacuum itself can respond, affecting the way particles and light behave. These effects are very subtle, but they match the predictions of quantum theory. Once again, empty space turns out to have structure, even if we cannot see it directly. Because space exploration deals with extreme conditions, these ideas sometimes appear in NASA research. Not as proof of unlimited energy, but as part of the effort to understand how space really works. When missions travel far from Earth, even small effects can matter, and understanding the vacuum can help explain things that would otherwise seem strange. Over time, the idea of zero-point energy has become something like a symbol of the unknown. It represents the part of physics that is still incomplete, the part where the equations work, but the meaning is not fully clear. Some people imagine it as a hidden power source. Others see it as a puzzle that may take centuries to solve. For scientists, it is simply one of the many questions that remain open. And that is what makes the subject so quiet and so fascinating at the same time. The vacuum is everywhere, but it cannot be seen. It has energy, but it cannot easily be used. It affects the universe, but it does not reveal its secrets easily. Somewhere inside that mystery, the story of zero-point energy continues, slowly, as science moves forward, one small step at a time. As physics moved further into the 21st century, the mystery of the vacuum did not disappear. In fact, the more precise the measurements became, the more carefully scientists looked, the clearer it was that empty space could not be treated as simple nothingness. Every modern theory that tries to describe the universe at its most fundamental level still has to include the energy of the vacuum. It may be small in everyday situations, but it never goes away, and its presence continues to shape the way physicists think about reality. One reason the vacuum remains so difficult to understand is that it sits at the intersection of two very different theories. Quantum mechanics describes the smallest scales of nature, where particles behave like waves and probabilities replace certainty. General relativity describes gravity and the structure of space-time, where massive objects bend the geometry of the universe. Both theories work extremely well in their own domains, but when scientists try to combine them, the vacuum becomes one of the biggest obstacles. Quantum theory predicts that empty space should contain enormous energy. Relativity says that energy affects gravity and the curvature of space. When the two ideas are put together, the result should be a universe very different from the one we see. Yet the real universe exists in a stable form, with galaxies, stars, and planets moving in ways that do not match the simplest predictions. This contradiction has been studied for decades, and no one has found a final answer. Because of this, the vacuum has become a kind of reminder that our understanding of physics is not finished. The equations work, the experiments agree with them, but the deeper meaning is still unclear. Whenever science reaches that point, researchers begin to explore possibilities that once seemed too strange to consider. Not because they believe anything is possible, but because the history of physics shows that new discoveries often come from places that once looked unlikely. Space research is one of the fields where this kind of thinking sometimes appears. NASA and other agencies are responsible for exploring environments that push technology to its limits. Spacecraft must survive radiation, extreme temperatures, and distances so large that ordinary engineering solutions are not always enough. Because of this, long-term research sometimes looks at ideas that involve the fundamental structure of space itself, including the properties of the vacuum. These studies are usually small and theoretical. They do not promise new engines or unlimited energy. Instead, they ask careful questions about physics that is not fully understood yet. Could the vacuum affect inertia? Could space-time behave differently under certain conditions? Could quantum fields influence motion in ways that are too small to notice in everyday life, but might matter in extreme environments? Most of the time, the answers are uncertain, but the questions are still worth asking. One reason the vacuum appears in these discussions is that it seems to be present everywhere. Unlike ordinary energy sources, which exist only in certain places, the vacuum exists at every point in space. If its properties could ever be understood well enough to control, even in a very small way, it might change how we think about propulsion or energy. This does not mean that free power is waiting to be discovered, but it does mean the background of space may be more important than we once believed. Some theoretical work has looked at whether the vacuum might influence the way objects resist motion. In normal physics, inertia is simply a property of mass. But in certain models, inertia may come from interactions between matter and the quantum fields that fill space. If that idea is correct, then every time an object accelerates, it is interacting with the vacuum. The resistance we feel would not come only from the object itself, but from its relationship with the background fields of the universe. This idea is difficult to test, and most scientists remain cautious about it, but it shows how the vacuum could be connected to very basic physical laws. If inertia depends on the vacuum, then the vacuum is involved in every movement in the universe. Changing that interaction would be extremely difficult, but even the possibility makes the subject worth studying, because it connects motion, energy, and space in a way that is not fully understood. Another place where the vacuum becomes important is in cosmology. The expansion of the universe suggests that empty space contains some form of energy that acts like pressure. This energy, often called dark energy, seems to push space apart on the largest scales. Some theories suggest it may be related to zero-point energy, but the connection is not clear. The predicted energy of the vacuum is far larger than what we observe, and no one knows why the difference exists. Because the vacuum appears in both quantum theory and cosmology, it becomes one of the key pieces in the search for a deeper theory of physics. Scientists hope that one day a new framework will explain why the vacuum has the energy it does, why the universe expands the way it does, and how gravity and quantum mechanics fit together. Until that theory is found, the vacuum remains one of the biggest unanswered questions in science. Black holes provide another example of how strange empty space can be. Near the edge of a black hole, the vacuum behaves differently because of the intense gravity. Quantum fluctuations can create particle pairs, and the strong gravitational field can separate them before they disappear. One particle escapes, and the other falls inward, causing the black hole to lose a tiny amount of energy. This effect, known as Hawking radiation, shows that the vacuum is not passive. Under the right conditions, it can produce real, measurable energy. Experiments with high-energy fields suggest something similar. When electromagnetic fields become extremely strong, the vacuum can respond in ways that make it behave almost like a material. Light passing through such fields can change direction slightly, as if space itself has properties that only appear under extreme conditions. These effects are very small, but they match the predictions of quantum theory, showing again that the vacuum has structure even when it looks empty. Because space exploration sometimes involves extreme conditions, NASA researchers occasionally study these ideas as part of broader investigations into advanced physics. Not because they expect to find a hidden power source, but because understanding the vacuum may help explain how matter, radiation, and gravity behave far from Earth. Even small differences can matter when missions travel millions or billions of kilometers. Over time, stories about these studies have grown into something larger than the science itself. When people hear that vacuum energy appears in NASA research, it sounds like proof that secret technology must exist. In reality, most of the work is simply part of the slow process of learning how the universe works. Scientists test ideas, reject most of them, keep a few, and move forward step by step. Still, the mystery remains because the vacuum is not fully understood. The equations predict more energy than we observe. Gravity and quantum mechanics still do not fit together perfectly. Dark energy has not been explained. And until those questions are answered, the idea of hidden energy in empty space will always feel like it belongs on the edge between science and mystery. So the story continues quietly, inside laboratories, inside equations, inside research papers that most people never read. Empty space is not empty. Motion never fully stops. Energy never completely disappears. And somewhere inside those facts, there may still be discoveries waiting, hidden in the background of the universe itself. By this point in the story, the idea of zero-point energy begins to feel less like a single theory and more like a thread that runs through many parts of modern physics. It appears whenever scientists look closely enough at the universe, whether they are studying atoms, galaxies, or the structure of space-time itself. The vacuum refuses to disappear from the equations, and every attempt to ignore it eventually brings it back again. That alone is one of the reasons the subject has never fully faded away. In earlier centuries, scientists imagined the universe as a collection of objects moving through empty space, like planets traveling through a silent void. Today, the picture is very different. Space is no longer just a stage where events happen. It has properties of its own. It can stretch, it can bend, and according to quantum theory, it can never be completely still. Even when nothing seems to exist, the vacuum remains active, filled with fields that continue to fluctuate at the lowest level, allowed by the laws of nature. One of the reasons this idea is so difficult to accept is that it does not match everyday experience. When we think of nothing, we think of the absence of everything. But in physics, nothing turns out to be something very complicated. The vacuum contains energy, but it is balanced so perfectly that we normally cannot use it. It affects particles, but only in subtle ways. It influences the universe, but it does not reveal itself directly. Because of this, the vacuum often becomes part of research into the most advanced areas of science. When physicists try to understand how gravity works at the quantum level, the vacuum appears. When they study the expansion of the universe, the vacuum appears again. When they examine the behavior of particles in strong fields, the vacuum shows up once more. It is always there, always in the background, like a hidden layer of reality that cannot be removed. For space agencies like NASA, understanding that hidden layer can sometimes become important, even if the results are uncertain. Space exploration pushes technology into environments far beyond what we experience on Earth. Spacecraft must operate in extreme temperatures, intense radiation, and near-perfect vacuum. Because of this, research sometimes touches areas of physics that ordinary engineering never needs to consider. In a few cases, theoretical studies have asked whether the properties of the vacuum might influence motion or energy in ways that are not obvious. These studies do not claim that zero-point energy can be used as a fuel, and they do not suggest that free energy machines exist. Instead, they explore whether the interaction between matter and the vacuum could produce very small effects that might matter under extreme conditions. Most of the time, the answer is that the effects are too small to be useful, but the questions continue to be studied because the physics itself is not completely understood. One idea that appears from time to time is that the vacuum might play a role in inertia. In normal physics, inertia is simply the tendency of an object to resist changes in motion. But some theoretical models suggest that inertia could come from interactions with the quantum fields that fill space. If that idea is correct, then every movement depends on the vacuum in some way. When an object accelerates, it may be pushing against the background structure of space itself. This concept is difficult to test, and it may never lead to practical technology, but it shows how deeply the vacuum may be connected to the basic laws of physics. Instead of being empty, space becomes part of every force, every motion, every interaction. Even if the effect is too small to use, understanding it could help explain why the universe behaves the way it does. Another place where the vacuum becomes important is in the study of the universe as a whole. Observations show that the expansion of space is accelerating, as if there is a form of energy built into empty space. Scientists call this dark energy, but the name only describes the effect, not the cause. Some theories suggest that dark energy might be related to zero-point energy, but the numbers predicted by quantum theory are far larger than what we observe. This difference remains one of the biggest unsolved problems in physics. Black holes provide another example of how strange the vacuum can be. Near the edge of a black hole, the intense gravity changes the behavior of quantum fluctuations. Particle pairs can appear, and one of the particles can escape while the other falls inward. The escaping particle becomes real radiation, slowly carrying energy away from the black hole. This process, known as Hawking radiation, depends on the vacuum itself. Without the fluctuations of empty space, the effect would not exist. Experiments with strong electromagnetic fields show something similar on a much smaller scale. When fields become extremely intense, the vacuum can behave differently, affecting the way particles and light move. These effects are tiny, but they match the predictions of quantum theory. Once again, empty space turns out to have structure, even when it looks completely empty. Because these ideas appear in serious physics, they sometimes become connected to more speculative discussions about the future. If the vacuum contains energy, people wonder if it could ever be used. If the vacuum affects gravity, people wonder if space could be controlled. If quantum fields exist everywhere, people imagine new forms of propulsion that do not require fuel. Most scientists remain cautious about these ideas, but the questions continue to appear because the physics itself is not finished. NASA's involvement in this subject has always been limited and careful. The agency studies many theoretical ideas as part of long-term research, especially when they relate to propulsion or fundamental physics. Most of these studies never lead to new technology, but they help scientists understand the limits of what is possible. Sometimes the result is simply learning why something cannot be done. Other times, the result is a small insight that becomes useful years later. Over time, the idea of zero-point energy has become something like a symbol of the unknown parts of physics. It represents the gap between what we understand and what we have not discovered yet. The equations say the energy is there, but the universe does not behave the way the simplest calculations predict. The vacuum affects everything, but it does not give up its secrets easily. For scientists, this is not frustrating. It is normal. Every generation of physics has had mysteries like this, places where the theory works, but the meaning is not clear. Those mysteries are what drive research forward, because they show where the next discoveries might be hiding. And so the story of zero-point energy continues quietly, not as a secret power source, not as proof of hidden machines, but as one of the deepest questions about the nature of reality. Space is not empty. Energy never fully disappears. Motion never completely stops. And somewhere inside the structure of the vacuum, the universe may still be holding answers that no one has found yet. As the journey through this subject begins to slow down, the idea of zero-point energy starts to feel less like a single mystery and more like a doorway into many different mysteries at once. The deeper scientists look into the vacuum, the more they find that it connects to almost everything. It appears in the behavior of particles, in the shape of space-time, in the expansion of the universe, and in the questions that still remain unanswered after more than a century of modern physics. One of the most unusual things about the vacuum is that it challenges the way people naturally think about nothing. In everyday life, nothing means empty, silent, still. But in physics, nothing is never truly empty. Even the most perfect vacuum still contains fields, and those fields never stop moving completely. The lowest energy state, allowed by quantum theory, still has motion, still has fluctuations, still has energy that cannot be removed. This is why the idea of zero-point energy never fully disappears from scientific discussion. It is not because anyone has proven that it can be used as a power source, and it is not because secret experiments have produced impossible machines. It stays alive because the equations themselves say the energy is there, and because the universe behaves in ways that suggest we do not yet understand the full story. The problem becomes even more interesting when physicists try to combine the two great theories of modern science. Quantum mechanics describes the smallest scales, where particles behave like waves and uncertainty is built into the laws of nature. General relativity describes gravity and the shape of space-time, where mass and energy bend the geometry of the universe. Both theories work extremely well on their own. But when scientists try to put them together, the vacuum becomes one of the biggest problems. Quantum theory predicts that empty space should contain enormous energy. Relativity says that energy should affect gravity. If both are true at the same time, the universe should look very different from the one we see. Yet the real universe exists in a stable form, with galaxies and stars moving in ways that do not match the simplest calculations. This difference suggests that something is missing from our understanding, something that future physics may eventually explain. Because of this gap, researchers sometimes explore ideas that once sounded too strange to consider. They look at the possibility that the vacuum might behave differently under extreme conditions. They ask whether inertia could come from interactions with quantum fields. They wonder if the energy of empty space might be connected to dark energy or to the expansion of the universe itself. Most of these ideas remain theoretical, but they help show where the limits of current knowledge really are. Space research occasionally touches these questions because space is the place where the limits of physics are tested. When spacecraft travel far from Earth, they operate in conditions that are closer to a true vacuum than anything on the surface of our planet. When scientists study the behavior of particles in orbit or the motion of objects in deep space, they sometimes find themselves dealing with effects that are too small to notice anywhere else. In those moments, understanding the vacuum becomes more than a philosophical question. It becomes part of the practical work of exploring the universe. NASA has never claimed to have a machine that runs on zero-point energy, and most scientists would say that such a device is extremely unlikely to exist. But the agency, like many research organizations, has occasionally supported studies that look at the deeper structure of space, simply because understanding that structure could one day lead to new ideas. Even if those ideas do not become technology, they help build a clearer picture of how the universe really works. Over time, the story of zero-point energy has grown larger than the science itself. It has become part of conversations about hidden physics, advanced propulsion, and the possibility that reality may be more complicated than we imagine. Some people see it as proof that unlimited energy must exist somewhere. Others see it as a reminder that nature does not always reveal its secrets easily. The truth lies somewhere in between. The vacuum does contain energy, but that energy is not like fuel waiting to be collected. It is part of the background of the universe, balanced so perfectly that it normally cannot be used. It shows up in experiments, but only in tiny effects. It appears in equations, but the numbers do not always match observation. It influences the cosmos, but its exact role is still unknown. This mixture of certainty and mystery is what keeps the subject alive. Scientists know the vacuum is real. They know it has energy. They know it affects the universe. But they do not yet know why it behaves the way it does. And until that question is answered, the story will never feel finished. When people imagine the future of science, they often think of discoveries that change everything at once. In reality, progress usually happens slowly, one experiment at a time, one theory at a time, one small correction to the equations. The mystery of the vacuum may not be solved in a single moment. It may take decades or centuries before the full picture becomes clear. And yet, the fact that the mystery exists at all is what makes the subject so fascinating. The universe is not simple. Empty space is not empty. Motion never fully stops. Energy never completely disappears. Even when everything seems quiet, something is still happening in the background. That quiet background, the restless vacuum, is always there, stretching across the entire universe, filling every distance between stars, every gap between atoms, every place where nothing seems to exist. And as long as that background remains, the question remains with it. What else might be hiding there, waiting to be understood? As we come to the final stretch of tonight's journey, the idea of zero-point energy begins to settle into something quieter. At the beginning, it sounded almost like science fiction, the thought that empty space could hold energy. that the vacuum might contain more than nothing, that somewhere in the background of reality there could be forces we do not fully understand. But the deeper we drifted into the subject, the more it became clear that the mystery does not come from fantasy. It comes from the equations themselves, from experiments, from the strange behavior of the universe when scientists look closely enough. Modern physics does not describe space as an empty void anymore. It describes space as something active, something filled with fields that never completely rest. Even in the coldest, quietest vacuum imaginable, motion still exists at the smallest level allowed by nature. That motion is what physicists call zero-point energy, the lowest energy that can never be removed, the background vibration of reality itself. This idea shows up everywhere once you know where to look. It appears in the behavior of atoms, in the radiation predicted near black holes, in the expansion of the universe, and in the equations that describe quantum fields. Each time, the message is the same. Nothing is never truly nothing. The universe always keeps a little motion, a little energy, a little activity in the background, even when everything else seems still. For scientists, this is not proof of hidden machines or unlimited power. It is proof that the laws of physics are deeper than they first appear. The vacuum has energy, but that energy is balanced so perfectly that it cannot easily be used. The equations predict enormous values, but the universe shows only a small effect. The difference between the two is still one of the greatest puzzles in science, and no one knows exactly how it will be solved. NASA's connection to this subject comes from the same place that all scientific curiosity comes from. Space exploration pushes technology to its limits, and when you reach the limits, you start asking questions about the foundations of physics itself. Could space behave differently under extreme conditions? Could the vacuum influence motion? Could unknown effects appear when fields become strong enough? Most of the time, the answer is no, but asking the question is part of how science moves forward. Over the years, small studies, theoretical papers, and advanced research programs have looked at these possibilities. Not because anyone expected to build a device that runs on empty space, but because the vacuum appears in so many parts of physics that it cannot be ignored. Understanding it better might not give us free energy, but it might explain why the universe behaves the way it does. And that, in the end, is what makes the idea of zero-point energy so strangely calming to think about. It reminds us that the universe is larger than our everyday experience. The silence of space is not truly silent. The emptiness between stars is not truly empty. Even when nothing seems to be happening, the background of reality is still there, quietly moving, quietly vibrating, holding together the structure of everything we see. It is easy to imagine that somewhere in that background there are answers we have not found yet. Not because the world is hiding secrets on purpose, but because understanding the universe takes time. Every generation learns a little more than the one before, and every discovery opens new questions that no one expected to ask. The people who study these things do not see the vacuum as magic. They see it as one of the last pieces of the puzzle, something that must be understood before the picture is complete. And until that happens, the idea will remain, always in the background of physics, always just a little mysterious, always just beyond full explanation. Tonight we drifted through those ideas slowly, following the strange path from quantum fluctuations to cosmic expansion, from laboratory experiments to theories about the structure of space itself. We did not find a secret power source, and we did not uncover hidden machines. What we found instead was something quieter, something deeper. A reminder that reality is more complex than it looks, and that even the emptiest places in the universe are full of motion we cannot see. If you enjoyed this late-night dive into hidden physics with Sleepy Tin Foil Hat, you can leave a like, subscribe, or write a comment telling me where you listened from tonight. I always like to imagine these stories traveling across the world, reaching someone in the dark, somewhere far away, listening while the mind slowly drifts off. Now there is nothing else you need to think about. Let the ideas fade into the background, the same way the vacuum fades behind everything else. Let your breathing slow down, let your thoughts loosen, and let the noise of the day move further and further away. Space is quiet, the universe is still. And even in that stillness, something gentle is always there, moving softly in the dark. Sleep well, and I will see you in the next one.